Hello reviewers, welcome to my channel Science and Technology. In today's show, Computer Wednesday, let's talk about what the heck is an SOC, what does it even mean? So let's dive deep into it. So we have to understand some history of it, is that we started to move away from vacuum puppies in basically 1960s. Basically, Saturn V mission. Basically, NASA development created IC knowledge that there is a very good chance there were some military contracts, but since they were not sharing, NASA is sharing. Let's just go with that. So you have to understand, vacuum tube was the biggest jump for humanity simply because we figured out how to do amplification without mechanical system. And this was a big deal because you can receive a weak radio signal and you can amp those puppies up. And that was a big deal because once we realized that, hey, wait a minute, we can have a signal taking a bigger action, we are like, hey, wait a minute, we can make logic gate, yes, AND gate, OR gate, NOR gate, all of those things were built with vacuum tubes. Now these puppies, you must have seen like Mythbuster and others, they are showing like, IBM used to have a computer where a byte was like this big unit you can pull out. Again, they had to make it repairable because these things, while they do work, they're not that robust. They're robust against EMP. Like EMP, this puppy is like, brah. Don't waste my time. They run on very high voltage. Like some of these puppy can easily run at 500 volts. Yeah, I have no idea like how shockingly high voltage these puppies are. So in some regards, they are robust AF. In other regards, they are fragile AF. So the idea is you can take a small signal and amp it up. Analog domain, meaning continuously variable signal, it can keep changing it. So once they figure out they can do that, they figure out digital circuitry and voila. So in 1960s, silicon technology comes along and people are like, we can make a transistor. We can do things with it. And then we slowly started to replace this puppy with that puppy. So we started to make small block IC. Be mindful, this is the era where our mindset is vacuum tube. So what a vacuum tube, we are doing that, okay, buy this transistor that does that, cool, awesome. But slowly we realize, hey, we can do more things to it. Like instead of having slowly putting diodes together and transistors together and making an AND gate or OR gate, what if that was made from the factory because you're gonna do that anyway? So we started to make these so-called blocks. Now blocks, again, had different needs, protocols. Like here's the deal. How do you think your calculator stores the number when it goes away from your screen? It has to store it, right? So that goes into shift resistor, original name. Algorithmic logic unit, ALU. Control blocks, basically how the heck you're supposed to do things, control block. RAM chip, it's a completely different chip. Clock IC, computers did not know what time it is. Time, and I do not mean time as in like exact time, like, date and time. Time as in like which frequency I am. So there is a different silicon that is only responsible for generate the clock signal. IO interface, how the heck you're gonna talk with a punch card and all that. That's a different IC. So this started to happen in 60s. This is what is going on in 60s. And everything was board based at that point in time. Meaning if you had taken the computer board at that time, it's like full of, like modern computer looks empty compared to this. Like why it is so much? Because everything is separated. Meaning there is no quote unquote CPU. There is logic unit, there is shift registers, there is short-term memory. Not if there was no long-term memory, so okay, it's a short-term memory. There were algorithmic unit. Basically, there is a card for plus, card for subtraction, card for division. Not that broken down, but like you get the point. Everything was what you call discrete. Like some people make a voltage regulator with LM317. I'm trying to make a LM317 by myself. So same thing. It was that everything was discrete. So everything was board with. That's why like this whole box, even though you might think compute wise, even your modern Casio is like, bitch please, but like this was full. And this era gave us the technological room that we are enjoying right now. The IT boom happened because of this, because this happened. And it affected few big peoples. One of those were Bill Gates. And yeah, this was a big deal. And again, even Apple's founder and other people, they are like, yeah, this was significant because before this, people were still stuck in the vacuum tube era. And be mindful, this and vacuum tubes existed at the same time. You could have easily gone into some institute and laboratory and military system. They might be using vacuum tube while this was also available. So fundamentally, this started to change that revolution. Again, let that switch over was happening. But again, if you spent billions of dollars making these things, you're not gonna throw it away. You're like, let's just keep using it as long as we can. So this is how the ball started to get rolling. Again, discrete IC. This is the era. So let's call it the 60s. So then we went into the 70s. Now 70s we started to go like, hey, instead of making blocks, what if we make discrete units? So Intel came along and Intel started 4004. This is a 4-bit computer, 1971. Things are looking up, good start. We had 60s, we have 70 now, good start. But here's the deal, 70 was turbocharged, as in like it was fast and furious with some extra booster, with some more booster. We have 4-bit computer released in 1971 and the 86 was released in 1978. 4-bit to 16-bit. And be mindful, the 86, if you're like, hey, I have heard this 86, yeah, that's x86. The architecture that you and I use most of the time in computers were created that time. So basically this was, basically people were moving. We went from not having anything to like, what if a CPU can do things? And this is the first time we went from, why limited to 4-bit? What if 8-bit? What if 16-bit? And this is the first time people were like, hey, what if we design things for 128-bit? Trust me, people were writing codes that could handle that. Again, mathematical, that was sorted. So more and more things went inside the CPU. And what do I mean by inside the CPU? Basically register. If you opened up a CPU of that time, basically 8080 is like address register. Register. Did I mention register? Microcode addresser, register, loading system, group decode ROM, bus cycle system. Yeah, be mindful. This in the back days, basically how do you access the RAM chips? It required a different board. Now it's like, okay, the CPU can handle that. Now, this still looks like a discrete, so many sockets. So idea is you have CPU here, you have hardware here, and then that's the RAM basically. That time they did not figure out that you can have RAM chips into a plate and then you can socket the plate. That was not sorted yet. So you could have actual RAM chips. If you have seen people on YouTube who was like doing ancient hardware repair and all that, you could literally take out half of the firmware of something if you remove half of the device. So, but again, this is the first time people are like, okay, what if we put everything that we can inside the CPU? This happened. And again, IBM computer, the PC started because of this. And this time, if you have opened the box, there was some room. Now, to be fair, it still required basically sound. You needed a sound card. See, this puppy could not handle sound. It could play back a file, quote unquote, but file will not play. So it had to go to a dedicated DAC, so to say. That was a dedicated hardware. Otherwise, this will go beep, boop, beep, boop. So for sound, you had sound. For video as in like encoding and all that. There was a text engine, by the way. So that was separate. All of those things still took some system, meaning this plate itself is not that useful. You still need to add some. But again, from last era to this is far more compact. This is like, bro, this is exponentially better. And this is the start of PC era, because again, we started to make CPUs that will look like CPU. We have the computer, literally the computer. And again, the architecture. So this is the first time system on a chip started to happen rather than having everything spread out. It's almost like we used to make bricks. Now we are making a wall, like we are shipping wall to you. We are still not making complete house yet at this era, but things have started to move that direction. Now, after that, progress speed kind of slowed down, but progress scope expanded. Again, that's why I said like we did not went from like, 4-bit to 32-bit very quick, 4-bit to 16-bit rapidly, but from 16 to 32 it was like, okay, take its sweet time. 32 to 62 is like, okay, we still don't use 128-bit. Again, it's unnecessary, people say. So again, we kind of reached a saturation point. But by 2000, things were sorted, meaning people have agreed to that we're going to have two paths. One path would be your SOC that is trying to do everything. This you use in your embedded hardware. ARM is still a company. Yes, ARM was there at that point in time. And ARM is going to make hardware using a RISC architecture, reduced instruction set architecture. But target is, it does everything. Basically, you open up your Nokia 3310, that puppy has one very big SOC that does everything. But it's not a powerful puppy. This is long ago. Like, this is so long ago. At that point in time, it used to count how many SMS you have. If spam was a thing, these things will not survive. They're like, bro, SMS memory full, SMS memory full. You had to clean SMS. I'm old enough to remember. Phone book was like 500, not even 500. If I'm not mistaken, this puppy had like 250. Comment me, like, it's too old memory for me. But it had 16-bit. By the way, Silicon was capable of 32-bit. They're like, okay, let's downclock it and all that. And again, that's why it has the efficiency. So it had modern technology of 32-bit. They underclocked it. parallelized it, and it's like battery. So 16-bit RISC architecture, and this was year 2000. It's not that long ago. And iPhone 2007, not that long ago. And this is iPhone, which is Samsung SOC, and that is the first time 90 nanometer system is, and this is a what you will call a big consequential SOC. Now be mindful, the silicon was already there because it's a Samsung silicon. And again, if I ever get a time machine, I'll go back in time and bitch slap Samsung's product manager. Can you imagine Samsung is the one that made iPhone? And not to mention just the SOC, they had the display, the camera module, everything. It's like, stop pooping out model. Properly take time with each model. There are 12 months in a year, only make 12 models. They should not have ever touched Qualcomm. That was the dumb idea. It's like, again, their hardware made the polished thing. How the heck they could not do it themselves if they ever gave them time? I'm pretty sure engineers are like, one model, sir, throw it away, new model, throw it away. So this happens in 2007, and this is the same time, basically your computer also goes through a revolution. Basically your CPU start to get dedicated GPU IC. Meaning it can now properly run a display, not just like, okay, I can give you some error commands and all that. No, it can run a GPU. So that started to happen in 2010. Die integration happened, and CPU now does more IO duty. I'm old enough, like my oldest computer, like a Core 2 Duo computer, it had like Southbridge. You will not find Southbridge anymore in the computers. They are like now integrated in the CPU, and more things are going inside the CPU. So the idea is, back in the days, there was a link between the CPU and the Southbridge. That Southbridge will do your SATA, USB 2, all of that. Now, all of that chip process compute went inside the CPU. So CPU has to actually talk. So either it can directly talk, but again, pin count becomes an issue. So nowadays they are like, okay, let's switch back to something, and soft switches. Basically, they're gonna send out PCI lane. You can switch on software, as in like the silicon wise. It's like, okay, this is for NVMe. This is for Thunderbolt. That's why if you see silicons, they will always say it's Thunderbolt or not. So we reached that point where it's like Southbridge died in front of me, and Northbridge is also almost gone. Meaning at this point in time, you can easily expect a server grade motherboard that's just like, there's no compute happening on the board itself, not even IO compute. It's more of like power management, feedback loop of like, you're not frying this or that, something like that. But you can have almost naked CPU taking care of most things, excluding power. So CPU is doing more, not only GPU, but other communication, IO devices. That when it's like Southbridge just disappeared. Like it just like, poof, go. So that's the progress. So x86 went on a route of like bigging bay fear, like it was a freight train, while this sort of RISC systems, they were like, okay, I'm mobile home, I can do everything. Not that great in anything, but I can do everything. So this is the progress that happened from like 2000 to 2010 era. Now we come to the current era. Now in current era, things changed. Intel pooped the bed for too long, continuously, and ARM had flexibility, because you have to understand that when Intel is making a CPU, they're stuck. They have to make CPU that every single vendor wants, meaning Dell wants it, HP wants it, Lenovo wants it, Gigabyte wants it, Apple wants it back in that day. Everybody wants it. That's an issue. But when you are going into ARM was very simple. Hey, we're gonna make the best core. We're gonna make a portfolio of cores. You're gonna buy the core. For example, Samsung can buy the core. It's like, hey, I think it would be good for us if you buy a lot of powerful cores and few efficiency core. Other companies are like, you know what, while everybody opens their mouth, is like, I'm gonna do turbo things. They're not doing it. Put 4 turbo cores and everything else is efficiency core. You can do that. And that tweaking allowed ARM to gain exponential momentum. It already had the advantage of taking care of everything. IO devices was a new thing for basically Intel to, okay, I'm taking the Southbridge. RISC processors, like, first time, like, we've been doing this, bro. So that switch, the fact that all of them can tailor-made their own CPU, they can put their own effort into it. It exponentially grew from, let's say, 2010 to 2020. ARM grew exponentially. And again, x86 was pooping too long. So over time, compute has now shifted from x86 to RISC. And RISC has now second advantage. RISC is not only coming from ARM holding side, that's one fire missile. Second is RISC-V. It's an open source architecture where you do not have to pay arms holding. And all major manufacturers, basically people who have the fabs, they are pouring money into RISC-V. So it will happen. And again, few hardwares have already reached into people's house. For example, many SSD, NVMe SSD has controller chip that is RISC-V based. And many microcontrollers that are entering the market is RISC-V. So that is also happening. So x86 is not on like, GG grounds anymore. That switch has happened. Again, it will take time before you see Intel fade away, but it will happen. Again, unless Intel creates some new architecture, which unlikely, why would they do that? And they have to make x86 very good, which they can't because they have to break compatibility, or they have to create a floating layer, which I have heard that they might be trying. Floating layer as in like just emulate it, basically what Steam does, but on a microcode level. Apple M1 was a big deal for this because it's the first time it's like, hey, every Tom, Dick and Harry says that they want to do everything, but people who buy Macs, they're writing novels in a coffee shop. It's a smartphone, just big keyboard and a screen, the end. They're like, they did it. They did it. They actually did it. And people are like, huh, that's it. We can do that. And then Microsoft is like, hey, we should do that. So that was a big deal. Very big deal from an ARM point of view, that a mobile SoC is actually same hardware as your computer. This was like a psychological switch you have to understand. Before this, everybody knew that this has the same horsepower as, I'm pretty sure, my second computer. Not my current one. My current one is badass, but this is there. This is capable. Heck, it even has USB 3. My first computer did not have USB 3. It had only USB 2.0. So it has the oomph. It just can't utilize it. Even though I can connect like keyboard, mouse, display, it does have USB display output. So I can connect all of those. It's just the OS will fight me because it's like, no, but you are a mobile phone. It's like, no, I'm a computer. You can change the scaling, screen size, elements, basically a software issue. And not even a software issue, it's a UI and UX issue. So Apple cracked that code. It's like, it's just UI and UX issue. Port the application, voila. And then we have some small things which made a big splash. Basically ARM have tailor-made, but what if x86 got tailor-made? Again, not to same degree as ARM, but some tailor-making. Basically AMD worked with Valve to design tailor-made SoC. That was a big deal. You have to understand, you do not generally do that unless you are a big player. For example, NVIDIA will design a custom chip for you if you are a console manufacturer. AMD will make most consoles, if I'm not mistaken, is AMD chips. But you have to place order like million orders. So this was not that. This was a shocking part. It's like, mildly, like, we have some money, how about do that? It's like almost like ARM level. It's like ARM does have like, big puppies like Samsung and Apple and all that buying it. But there are also small puppies that are buying it. It's like, yeah, we sell few million, can you give us? ARM is like, yeah, pay the license, have fun. So Valve did that. And it was successful. And it was so horrifyingly successful that basically Valve went from, I have no idea how hardware works, to, oh yeah, we make our own custom SoC and we are so goddamn good at gaming industry that everybody is suing us for monopoly. And to be fair, it's not Valve's fault, everybody else is brain damaged. So I don't blame, useless or meaningless politicians to like, oh, let's sue Valve. It's like, it's the only company that's caring about customer. Only company. So again, that's why it was successful. And this also created another shock where it's like, hey, you can float the instruction set. This floats x86 instruction set. Is like it runs the game without being x86. Oh, sorry, I mistake the hardware layer. It does that on a software layer. Basically, it runs the Windows layer, DirectX on Linux layer. So this changed the software, this changed on a hardware level, and this created an era where people realized that compute has become powerful enough that you can float whatever you want. Like you can float microcode if you want to. So. And laptops also became very powerful in this time. This is one good thing that happened in x86. If you have bought laptop around 2010 plus to 2020 era, you must have noticed like most laptops have super duper hyper crappy GPUs. Like you could not even launch a game, let alone watch. Like if you were got your high resolution HDR video file, it will struggle to play that. And if it's a modern format, it's like good luck with that. So there was a very serious time where it's like, it is really difficult to have fun with a laptop that just have the CPU, because the GPU on it, on that die, is very poo-poo. But after 2020, We are getting quality GPUs, as in these GPUs are so good in contrast that if you go a few years ago, you had to buy a dedicated GPU that would be the lowest end possible and still would be crappy experience compared to what you can get nowadays. Like nowadays, if you are getting a silicon, it has enough GPU that it's no longer like, oh, don't open a game. It's like, yeah, you can open a game and you can even play at full HD, but don't expect 4K 120 FPS. Like we had that switch. I'm alive enough to remember that phase. So we are entering in an era where one die can do it all, meaning you can have one silicon, like, bro, I can take that. I can take care of the GPU, I can take care of your NPU, I can take care of your encryption, all of that. And again, exponential growth of ARM because of competition and flexible manufacturing went YOLO. Now we have come to the future. Basically, there is a point. Be mindful. You might want to integrate everything, but there is a point. You do not want to integrate too much. For example, if you ever opened a hard drive, there is a BLDC motor driver. If you watch a very old one, you could easily see where individual MOSFET is. Nowadays, you will never see it. It's a one chip that is like, I control the whole motor. Basically, there is a feedback loop from the controller and it's like, I got this. But again, there is a penalty of that. For example, when you're talking about phones and all that, from a manufacturer's point of view, graphics units and RAMs, they are a SKU option. For example, Samsung wants to have the option where it's like, hey, we have this motherboard that we are making for our phone. I think it's called mainboard. We are making this mainboard and we're going to give 4 GB option, 6 GB option, 8 GB option, 12 GB option. Do not ask me why Samsung has this much loose motion, but they do. They physically have model that has 4 RAM SKUs. So I have no idea why, but they do. So SD, they want the ability to swap out RAM chips. And again, based on every company that has that ability is very happy right now because they could tailor based on the RAM crisis and all that. So they can do that. GPU on a computer is a very big deal because it's a very disproportionate thing. Meaning, if all you're doing is gaming, you may not need the latest and greatest and a GG CPU. It's like, you can have fun. Like, again, it won't be like greatest experience, but it will be fun. For example, I did this. Like, I literally had Core 2 Duo, then I upgraded to FX8350. Again, my GPU remained the same. I carried forward one GPU, and then I was like, okay, my GPU is not great. It was ATI long before AMD bought it. So I replaced that with GTX 1070. Voila. You could not do that if everything was inside the silicon. So fundamentally, there is a penalty for a company's point of view, where it's like, if they make everything in one silicon, they also get stuck. For example, ARM has the advantage, like any Tom, Dick and Harry can buy ARM license and be like, okay, I'm going to make a silicon as I need it. Be it Amazon, be it Google, they can make that. It's like, hey, because we are running a server, give us the best bang for buck. Basically, just give me oomph of power. Efficiency, I don't care. Just give me the power. They can do that. And again, mobile players can do the opposite. It's like, hey, I do not need GG amount of compute. I just give me basic. They can do that. But if you integrate everything in one silicon, the company gets stuck. It's like, okay, what can we do now? So there is an issue. And be mindful, there are two forces that are going against each other. For example, the more basically integrated you make it, the more profitable the device becomes, but more harmful it becomes for the planet because it will have shorter lifespan. Under known laws of physics, under known laws of market forces, it will have a shorter lifespan compared to a dedicated device. So fundamentally, the more SOC can do, the more black box it becomes. It's like, it's the thing, either it works or it does not work. It's a black box now. Now, if you basically just keep doing that, everything, the moment any minor update happens, you have to throw the whole thing away. Meaning you could have Apple system and you would be like, bro, I bought this 8 gig model, it's great, it's awesome. But there are Apple software that is like, bro, you have to have 16 gigs, otherwise it will not run. It's like, okay, I'm going to swap the RAM. Oh, swapping RAM is not an option. You see the problem? So companies want to flood the market. We have one planet. So there is these two things are going boom, boom with each other. So we have to balance these things. We do not want to force everything. And there is a good reason for that. Even though everybody tell you is efficient, yes, it is, but it does come with a penalty. Lifespan shrinks. For example, your software changes. For example, if when I bought GTX 1070, imagine that GTX 1070 was integrated in the silicon, the CPU. I have to throw away the whole CPU. But now I don't have to. When I switch from basically H.264 to AV1 codecs, that's a completely different software package, but does require a dedicated silicon. I can just eat the GPU and tada, What if in future somebody creates a new codex, HAV2, let's just say. I don't have to throw away the computer. I have to just swap out the GPU that supports that. That's a very easy thing to do. And not to mention security system. For example, many servers have a chips that is just for security encryption. And if it gets outdated or cracked, you throw away the chip, put a new one. You must have seen Windows did something similar with like a certain motherboard had that, not every motherboard, but it can be done. You do not want to integrate everything in one system because then it becomes throw away the whole box. Now it's like, so for me, there is a reason where software evolution and hardware security vulnerability evolution would ask you to replace just one thing. But if everything is inside the silicon, you can't do much. So fundamentally, we have to balance it. For example, it's now a question. For example, somebody gives you, let's say, framework 14, why I'm saying, framework 13 Pro. And it's like, okay, this laptop will only give you lifespan of, let's just say, 15 hours. Versus you can buy Apple that gives you lifespan of 20, battery-wise. Cool. But here's, I'll still choose the 15 one. Why? Well, I know in few years from now, it will still be useful. How do I know that? Because framework 13, 5 years ago, still is upgradable. Like if something happens, like let's say screen crack, which is a normal thing, battery wears out, it's a normal thing, RAM requirement changes, it's a normal thing. I could tank all of that. In Apple, throw it away. So fundamentally, that's the thing. For example, your mobile phone have a lot of advanced compute in the SOC, so it does that 5G encoding and all that. And it is inside it. Cool, awesome. But here's the deal. If everything is inside, company manufacturers are stuck. For example, as you know, every Tom, Dick and Harry is working on making sure that we can have 5G from space, as in like satellite phone in our normal phone. Can it be done? Physics is done, sorted. ATS Space has already done that with your normal phone. And Amazon is also trying to do that, and so is SpaceX. It will happen. Most issue is with a license and other rocket launch cadence. Other than that, things are sorted. But here's the deal. I can guarantee you, the moment that becomes a thing, let's just say by 2030, it becomes a thing. It's just a thing that you do. I can guarantee you SOC engineers will work their ass off. They will have a new module that is for that. And again, it can work with this, but it's like if you have this module, it would be far more efficient. Manufacturers will be like, bro, we already placed order for 1 million of the old chips. We are stuck. Again, from manufacturer point of view, they will be stuck. So you can see that, like we have platform power management IC that is also going inside nowadays. Then we have a radio frequency, audio codecs, fingerprint encryption. Everything is going inside. So that means nothing can be changed. You have to throw away the whole thing. Again, from a manufacturing point, it does matter. It's like you have to know what something in future would be launched, and you have to place the order based on hopes. So again, they can work with it, but again, we can't afford to upgrade phones every 2 years. So we have to balance it out. It's a good thing, it's a good progress, but we have to, like, you know, maybe we are going bit too much black box. How about we pull back a little bit? So we have to be balanced about it. You cannot just go YOLO on it, because again, hardware will change, software will change, and you have to throw away the whole thing. So this was my presentation on basically what the heck is a SOC, that evolution, whole evolution. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me out. If you enjoyed it, please click the hype button and press the dislike button if you did not like it. I would urge you to press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.